Everyone, my name is Heather McConnell. Today I will present to you my Project 2 for Data Analytics Fall 2024. This is an analysis of the Breast Cancer of Wisconsin dataset. Our primary objective is to build a predictive model that can classify breast tumors as malignant or benign using features pertaining to the structure of the tumor. These features include measurements such as radius, texture, perimeter, area, smoothness, compactness, and symmetry. The first step is to explore the dataset in order to understand it, its size, and its features. This dataset contains 33 columns or features and 569 rows or data points. Before performing the analysis, we need to clean the data. Our initial step is looking at the information here, checking out the data types, and checking for null values. And then after finding null values, we delete those columns containing the null values. We're also deleting columns and features that may have NA data as well. Next, we use box plots to visualize the distribution of numeric features as malignant, represented as a M, or benign, represented as a letter B. Box plots are a great way to quickly visualize the data's distribution and variance of each feature. We can easily see if there are outliers present. I'll get back up to the top here. And we can easily compare the median values as well. Features with distinct differences between classes may be good candidates for our prediction model, like in this example, the radius mean. And those with very similar distributions may not be as good candidates. And we can see this is a great example, and so is texture. They're very similar. So we can quickly kind of compare and get an idea of which features we may want to keep and which features we may need to drop. Next, what we want to do is make sure and to be as precise as possible of which features we want to drop in this data set. To do this, we're going to use the ANOVA F test to select the most relevant features. This is going to help us increase the accuracy for predicting the tumor diagnosis. Okay. The ANOVA test does this by identifying which features have significant differences in their means across classes. So higher F scores will indicate more significant difference between classes, while lower P scores signify statistical significance. So features with low F scores and higher p-values are often removed as they contribute less to the prediction. So kind of going through some of the steps here for the ANOVA test. What we needed to do first is to create a numeric feature from the diagnosis feature. Since diagnosis is represented by M and B for malignant and benign. To do that, we simply map M to now be represented by 1 as a true value or malignant value, and B is mapped as 0 or false. This is very important so that we can work with the data numerically in the steps to come. And here within the ANOVA test, we are selecting the features with the highest F-score, and we're going to take the top 5 features with the highest F-score and use them for our model. So here is the output of our ANOVA test. And we can quickly see which features are more significant to this data set. And the top 5 are the ones we're going to keep. So we can see that the F-scores are much higher, with concave points worst, and getting much smaller as we go down. The p-values are pretty similar until we get towards the bottom, but you can see the correlation between the low F-scores and the higher p-values. So those are features that we would definitely drop. They would be less significant. And that's what we do in our next step. We're taking those top 5 highest F-score features and we're putting them into their own data frame so that we can work with them in our prediction model. Next, we create a correlation matrix. The correlation matrix helps measure the relationships between the different features in a data set. So it's showing the strength and direction of linear relationships and allows us to identify highly correlated features which typically could be considered for removal to improve interpretability and reduce redundancy. So an example might be looking at the perimeter mean. We can see that perimeter worst has the highest correlation. So that might be a feature that we would potentially want to drop one of them, depending on which one is more significant or less significant to the data set. Okay, now that the data is cleaned and we've dropped features that are not as statistically significant, or we've reduced our data set, making it smaller and more manageable, we're going to build our prediction model. To do this, we use the k-nearest neighbor algorithm to develop our prediction model. This algorithm works by finding the k closest data points to a new observation and predicting its class based on the majority among those neighbors. So to evaluate the model, we used 10-fold cross-validation. This means splitting the data into 10 parts, training the model on 9 parts, and testing it on the remaining part. Then the process is repeated 10 times, and we calculate the average accuracy to get a more reliable result. We also test using only odd values for k, in this case from 1 to 15, to avoid any ties when predicting the majority class. So our result here shows that when k is equal to 3, we get a 95% accuracy rate. In conclusion, our analysis used the ANOVA F-test for feature selection, reducing noise in the dataset by retaining the top features. Then we built a KNN model and optimized its parameters to achieve the best predictive performance. In this, we achieved 95% accuracy with this prediction model for breast cancer prediction. I hope you enjoyed this presentation, and thank you.